Hello people, we have here an object is doing a uniform circular motion. So is there a net force acting on this object? Definitely, because according to Newton's first law, if the net force is zero, this object should be traveling along a straight line at constant speed. In the previous video, we have already learned that an object in uniform circular motion is actually always accelerating towards the center of the circle. So to have a centripetal acceleration, you must have a centripetal force. That's Newton's second law. So what does a centripetal force do? It keeps changing the direction of your velocity without changing your speed, because it's acting perpendicularly to your velocity all the time. There's no tangential component. If you think in terms of energy, it also makes sense. Remember, the work done by the force is zero if the force is perpendicular to your velocity. So this explains why even though you have a force, there's no change in the KE because there's no work done. I'm getting a bit giddy. Let me explain using this static picture instead. So for a uniform circular motion, you are continuously having a centripetal acceleration, which means you must continuously experience a centripetal net force. But what is the magnitude of this centripetal force? Since the centripetal acceleration is given by v squared over r, or if you prefer r omega squared, that means the required centripetal force to keep something in uniform circular motion will be just mv squared over r, or if you prefer mr omega squared. Then here comes a question. Doesn't that mean that it's very difficult to achieve uniform circular motion, since the centripetal force, not only must it be always acting in the correct direction, it must also be having the exact correct magnitude? Actually, uniform circular motion is really easy to achieve. For example, if you tie a stone to a string and swing the string around, you can keep the stone in uniform circular motion. And then you ask, why is the string so clever? How does a string know that it must exert exactly this amount of force? Okay, let me try to explain. So this is the stone tied to the string. So at this moment, you're having this velocity. If the string doesn't do anything to the stone is going to travel along this straight line path, which should mean that the string has got to be longer. So if the string is an inextensible one, then naturally it will exert a tension force on the stone. And guess what is the magnitude of this tension force? The string will naturally exert a tension force that's just the right amount, so that the stone will go round and round along a circular path whose radius matches the string's length. In fact, if you swing the stone faster and faster, the string will also have to pull harder and harder. And if you swing it at too fast a speed and the string cannot support that tension force, then the string will just snap. And what happens to the stone? It will stop doing the circular motion. It will just go back to its straight line motion. Let me give you another example. So this is a merry-go-round that's spinning around at an angular velocity of omega. So if you're sitting on a merry-go-round, then you will be doing uniform circular motion, which requires a centripetal force of magnitude mr omega squared. So where does this centripetal force come from? So this is the merry-go-round, and this is you. This is your butt. Left on your own, your butt will want to travel along this straight path. But the merry-go-round surface underneath your butt, the surface underneath your butt wants to travel along this circular path. Now the merry-go-round surface will not want that to happen. Why? Because of friction, Remember, friction always tries to stick two surfaces together. So if your butt is here and the floor is here, the floor wouldn't want your butt to be here and the floor to be here. So naturally, the floor will exert a frictional force in the centripetal direction. And what is the magnitude of this frictional force? mr omega squared. The magnitude of the frictional force will be just enough to maintain you in the same circular path as the floor. In fact, if you spin the merry-go-round faster and faster, the frictional force will also automatically increase. But there's a maximum frictional force, right? So if you spin it too fast and the frictional force is insufficient to keep you in the circular motion, then what happened to you? Your butt will go woo! Okay, in summary, uniform circular motion requires a net force that's in the centripetal direction with magnitude mv squared over r, or if you prefer, mr omega squared. I want to stress that it's the centripetal force that results in the circular motion, not the other way around, yeah? Don't ever develop the misconception that the circular motion is the cause of the centripetal force. For example, when you swing the stone round and round, naturally the string will exert the tension force, and it's the tension force that provides the centripetal force that results in a circular motion. Likewise, in a merry-go-round, we have a situation where naturally the frictional force will set in to provide the required centripetal force that results in a circular motion. The tension force and the frictional force did not result because of the circular motion. Instead, it's the tension force and the frictional force that results in the circular motion. Get it? Okay, ta-ta!